Hey everybody, this is Larry. This is day 6 of the Leetcode January challenge. Happy New Year, even though I guess it's been a week. Is that too late? I don't know. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Cave missing positive number. Okay, given an array of positive integers sorted in strictly increasing order, so that means that they're unique as well because they're strictly. And the number k, find the k positive. Okay. I mean, the constraints are low enough that I would say if I was in a competitive situation, I would probably just do a for loop and it'll be O of n or O of k, depending on the constraints exactly. And that'll be fast enough, even up to like a million, right? You put all the numbers in a set, you just do a for loop. You know, you have no chance of having off by ones or anything unless you're really silly. But that said, the thing to take advantage of for this problem is that it is there's already an order to it. Then that means that we can exploit this order a little bit, and knowing that it is strictly increasing, because if it is just monotonically increasing, meaning that there are duplicate numbers, then you cannot make some assumptions that you can make with strictly increasing, right? Because if it is strictly increasing, that means that well, what does that mean, right? And this is positive. Okay, yeah, because if it is strictly increasing, that means that if there's no number missing, well, every array of length n is going to look the same, right? Because it's just going to be 1 2 3 4 5 dot 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 n, right? And what does that mean? That means that at the fifth position, for example, the number is going to be 5 and so forth. And I think this is hopefully straightforward. With I position, the number is I, right? And this is one index, of course. We could do some math. It's not a hard math to make the translation. And as a result, now we have a function that, or hopefully you should see a function that has this relationship where, okay, if there are two numbers missing, say, if instead of 5, this is a 7, that means that there are two numbers missing ahead, because there should be a 5 there, but now this is a 7. Yeah, so that means that the two number missing before 7, right? Yeah, and in this case it's a 5 and a 6. But I think using that kind of logic, you should be able to binary search the cave missing positive integer, because that it's going to be a monotonically or strictly monotonically increasing sequence where because if you look at the prefix answer, it's going to be 0 number missing, 0 number missing, 0 number missing, maybe 1 number missing, 2 number missing, and so forth, right? And that sequence, if you think about it, it's not going to go down, right? You're not going to be like, oh, there's 2 number missing, but then later on it filled one back in and then have 1 number missing. So that curve is always going to go up, and from that's enough to binary search. And as a result, it is a very good exercise to just do binary search in general. At least I always think of it that way, because I always feel that off by one's a little bit tricky. So let's do it together, and we'll go for the bounds together. Let me know what you think. So binary search, what I get questions is that what templates do you use and stuff like that. And sometimes I do go over this a little bit fast, but I just ask myself a couple of questions, and those questions will basically dictate how I write the binary search code, and that's pretty much it. Yeah. Okay. So I always write something like left and right for left pointer and right pointer. In this case, I guess the left should be 1. Right. Well, okay. Let's figure out what our function is supposed to be first, right? Let's just put them numbers. Well, our binary function is, and that's where you have to ask yourself very precisely, because otherwise, off by ones. Like if you ever struggle with off by ones with binary search or even other things, it's because you didn't define your questions, which means your quote unquote your code and then your invariants carefully, because they're all related, right? Here we want to say we have a function. So the template for binary search is going to be okay. Um, so yeah, so we want to ask ourselves, given a number n, um, how many numbers are missing before, and is it k or larger, right? I put. I guess this is more like two questions, but it's actually just one question. Is it? I think the better question is, but this is more implementation-y detail. That's why I phrase it that way. If you really want a more precise question, it's probably just given a number, and are there k numbers missing before? Are there k numbers missing? Right? I guess the before is a little bit weird. And that's basically how I would think about it. And then now I write something like, the reason why I want to define this is because then now we have to define the left bound and the right bound. I always like to make left and the right inclusive in my search. And what I mean by that is that left has a possibility of being true, and the right has a positive possibility of being true, right? Um, and k could be 1. Okay, I mean, I thought it maybe could be 0, it doesn't matter. But here, and because of the nature of these things, it's actually okay to um to have like an infinity, right? Because infinity would have the same, you just need a function that if the input is, well, not actually infinity, but like effectively infinity, some big number, it still gives you a reasonable value. So here, yeah, let's just do that instead. I'm going to do something like a billion. And as I said, this bound should be inclusive, so that if left is equal to right, then we're done, because that means that the inclusive range only has one number left. And that's why I write it this way. I always write, and this is just standard getting the middle number. I understand that there are other ways to write this so that it doesn't overflow in other languages, but for me, I just kind of write like this so I could keep it simple for now. But yeah, and then now I have a function if good of mid. Well, what is good, right? Well, we have this k numbers missing. So the answer is, if there are k numbers missing, that means that, what does that mean, right? If there are k numbers missing at this point, k or more, that means that we want a smaller number, because, well, if you get a larger number, it's only going to be even more number missing, right? So that means that it's going to be on the left side. And yeah, so then that means you want to set right to the mid. And we set it to the mid exactly because in this case, that means that it is still good. That means that right is still a good possibility because it has at least k numbers missing, right? Else, we said left is equal to mid plus 1, because if this is no good, we know that mid cannot be good, so we have to move 1 to the right of that, right? And we move to the right by changing left. And then at the very end, I think we can just return left or right. It doesn't really matter because they should be the same. That's the invariant of this loop. And then now we just write the good function, right? Good for some x. I guess I think I like the term x, but maybe it could be target or something like that. And this is just basically what we said, right? It's I mean, at the basic level, that's basically what we want to do, but we want to also make sure that there are edge cases and we handle it correctly. And what I mean by that is, okay, so let's say we had our funkiness 1 2 3 4 7 like we had before. Oops. Right. And x is 7, right? Well, we can't really find a 7. So sorry, I'm just giving a quick thinking because I don't want to say something wrong because I know how to do it. But basically, what you want to do is okay, and I'm trying to figure out how to map this to this in a good way. And of course, given that it is in increasing order, you can actually binary search for that as well, and then just do the math before that. Um, but I think that maybe is a little bit too weird or complicated. So, and I don't know that I want this to be the index of the array. So that's the part that makes it a little bit awkward for me. Um, hmm. At least just in terms of implementation detail, because I think it's not so bad. Um, hmm. Then you have an array of yeah, no, I mean, I think I'm just debating about the possibility of using the index or x as the index of the array instead like this. But I still feel like that's a little bit yucky. So, and of course, we cannot pre-process array because if we pre-process it in any way, that already makes it linear, right? Um, and that kills the point of doing this binary search if you do anything pre-processing that makes it linear. Um, Unless you do it multiple times, but that's pre-processing another story. So, do I really want to do? Do I really have to do two binary search to this? I think part of my reluctance is just me being a little bit lazy of writing two binary search, but it's really not a big deal. Um, okay, I guess I'll just do binary search. But in this case, for the sake of me being lazy, and maybe we'll go over some stuff afterwards. But the thing is that if I make this a binary search, this actually makes it log square of n, or depending on how you want to call it, log n log u or something like that. So that's a little bit. Hmm. I guess the index has to be the way to do it if you want to keep it in log n. It's just that the math is a little bit trickier because then now we have an index function and then we have to get um, and then we have to do some conversion, and that's fine. I think we'll do it that way then because I think we want to keep it in log n. Okay, yeah, okay, but now we have to change this so that given an index x, yeah, are there k numbers missing? And then here now we change it to the length of the array because obviously the most you can go to the right is the length of the array, right? And then now we just return array of x minus x, and this is zero index, so then we have to minus well, we definitely have to minus one. Yeah, and then we check whether this is bigger than or equals to k. So then now this actually gives us the first index that has k numbers missing, I think, or or um, or n, where n is equal to the length of the array. And then now we have to do some math, right? Now we left, this would still converge to the same thing, but now left is an index, right? So, okay. Now we have to do some maths. Okay, so array of left minus left minus one, maybe that's a little bit yucky. So this has, you know, missing is equal to this thing. We want to and again, this could be out of bounds. That's why we have to check for it. So let's check for that. If left is equal to the length of array, that means that the biggest number is going to be, or the missing number is going to be bigger than the biggest number. Um, So what does that mean, right? So that means that we take the last element, we we add, and this is just math, right? We add k minus um, minus n. No, the other way around. So we want, and I think this is just something that you could do on a paper. So if you're not following through, that's my fault. But yeah, but this is just the length of the array minus this thing minus the last element minus 1 plus k, um, and that should be, is that true? No, I don't think so. So yeah, I think this is just doing it on paper, to be honest. Um, and the last element. So basically, what is the offset, right? The offset or missing is you go to the last element minus the last index. Yeah, I had it wrong the other way. Sorry, minus 1. So that's the numbers of things that are missing. Except for that, should be minus. This should, the last element's index should be n minus 1, right? So this is n minus 1, so it's minus 1 again for correcting it from zero. From 0 index to 1 index, and then now we take k minus missing is equal to the offset, and we just want to return the last element plus offset. I think that's maybe right. Maybe we're off by 1 here, but that's what we'll check. Otherwise, we do this thing. Um, then offset is equal to k minus missing again, and then we just return array of left plus offset. Maybe off by 1, but let's play around this. And also let's put in the other one. Oh, they gave you that test case, so that's nice. Well, off by 2 is a little sad. Um, hmm. Hmm. I mean, there's really nothing to look at. It's just, I think, so I knew it was going to be off by 1 a little bit because I know that we didn't take account the last number as the number that's off, but hmm. The off by 2 is a little sad though. I mean, this is clearly 6, so why do we have 8? Because we take the last index. Last index is 5, or we should get, oh no, we should get 4 actually, right? Yeah. Is that true? Yeah, it should be. Actually, I don't know if it's possible to get to 4 because of the off by 1s. So let's do this. Oh no. Oh yeah, of course. Actually, this should be minus 1, but then but then this would never happen, right? So we actually, that's kind of why I wanted to avoid this earlier, is because there's so many possibilities for silliness. I think then this is not possible, so, and that's fine. But yeah, why does this give me 10? Because, okay, given 5, let's just print out some debugging. Again, this is off by 1. It's which is kind of just unfortunate. Okay, so left is equal to 3. Okay, so this is what I expect actually, so that's good. And it's just 2 plus this, so, but we might have to test I want to test something like 2. Yeah, I suspected this would be a little bit off. Um, Clearly 7 is a number in it, but this is exactly um, this offset would be 0, which doesn't make sense because offset always has to be 1 or more, right? Um, eh, just a lot of off by ones. Okay, so this is 11. Hmm. But that means that the offset is -1, which is not great because we expected this to be. No, I mean I think that's we wanted the first number, which is I think actually this is what we expect. Um, I did it wrong. Um, yeah, I think that's why we have two cases. But because we wanted the array element to be equal to um the first number in which is bigger, right? So we actually want something like um, but now there's so many edge cases. Um, we actually want something like this. Um, oh, whoops. But I know that this is going to mess up the other ones. Uh, ooh. Why does this give me 11? Offset is 4. Why? Tell me why. Oh, the missing. No, it's okay. So 7. Hmm. Now let me think about this. I think I want to change the way that I do the binary search. Now instead of are there k numbers missing, um, now it's a little bit awkward the other way as well. I think I want this to be strictly. Maybe that's part of it. Because if it is equal, then that's not good. Okay, so I want that. That's 1. That's not going to fix it enough, but it's going to be a fix regardless. And then now, so now this is 11. So then now we take 7, and what is missing on 7? Why is the offset 4 from 7? So the missing is equal to only one number missing now. So 4. So this is 7 minus minus 3. Oh, whoops, I'm just being dumb. So we want to subtract that from. Well, we want to we want to subtract that from the index plus 1, because it's one index to convert it to one index. And then why do I have a -1 again? Okay, so we finally got this one right, but then now, but the thing is that what we don't take account here is that we go beyond, right? So actually, maybe we can here now go back to this thing. Oh yeah, but then it may go out of range. I think this is okay, but we just haven't have to make we have to do a case where if it goes beyond the beyond the biggest number. This is wow. This is messier than I expected, to be honest. So yeah. So if um, what are we checking? Okay, so if the last element, okay, if left is equal to the last element, then we have to do some checks. Because if this is the last element, then we have to check whether we have to go before or we actually mean after. And sometimes you can now I think we can actually convert this to this, and I think maybe that works well. It's just that I was printing it stupidly. Okay, so this is okay finally. We have to figure out the offset 0, 0 case, which is what I thought I took care of when I changed this to um, whatever. But yeah, I think I just have an off by 1 here as well because now okay. Hmm. Oh, maybe this has to be greater than you go to then. Okay. Yeah, if this part is a little bit hard to follow, that's my fault. I think I just didn't, as I was saying at the beginning of this video, you really have to define what your functions are, and I did not do that correctly the first try. That's what makes this a little bit annoying to get right. But let's give it a submit before. Oh, I should have tested small numbers. Um, but but yeah, okay. Um, but yeah, I think that's where you have to declare, your functions very specifically. And give an index. Are there k numbers missing? Yeah, okay. Um, and the reason why is because then now we could think about the bounds. And if there are k numbers missing, that means that you actually want the number before, which is what I'm doing here with all this stuff. And then doing the index that way. If you want to write this as actually -1 plus 1, which is why it was a little bit confusing. But having the ability to visualize and I think this is why if you're practicing debugging as well, when you have these statements, that allows you to see what's up because like if the numbers don't turn out to be where you expect them to be, then you're doing something weird. Okay, so in this case, because we're doing binary search, this loop will run log n times because we choose the bound to be n. And that's pretty much it. In terms of space, it's clearly all of 1 because we use constant number of extra space. And yeah, this is really annoying to get right, especially since you have to do some formula afterwards, transformation formula, at least the way that I did it. What is the hint? Keep track of, yeah, okay. Oh, that seems like as you scan the array, like, that's a linear time algorithm. But I wanted to do it in log n, right? Because if it's linear, I would win in a for loop and that's it. And then that would be a really short video. But yeah, let me know what you think. It's a little bit early, and I will see you tomorrow. Bye bye.